Let's talk about sound. You hear it every single day. Someone calls your name across the room, and you turn around. A car horn blares behind you, and you jump. Music plays from a speaker 10 feet away, and somehow the rhythm reaches your ears perfectly. You've experienced this thousands of times, so you must understand it, right? Okay, explain it to me. What actually happens when I clap my hands right here, and you hear it over there? What moves between us? Most people say sound waves, like that's an answer. But what is a sound wave? Is it a thing? Does something travel from my hand to your ear? And here's what really gets interesting. Why does it need air at all? You've heard that sound can't travel in space, in a vacuum. But why not? What's so special about air? What is air actually doing? See, you think you know what sound is because you hear it constantly. But if I asked you to explain how my voice right now is reaching you, really explain it, you'd realize something uncomfortable. You don't actually know. And that's exactly where we need to start. Here's what your brain does automatically. When you hear a sound, you imagine something traveling, like throwing a ball. I throw it here, it moves through space, you catch it there. Simple. Your brain wants sound to work the same way. Something leaves the speaker, crosses the room, enters your ear. But here's the first problem with that picture. What exactly is the something? A ball is made of atoms, of matter. You can hold it, feel its weight. What's the sound made of? You might say vibrations or energy. Okay, but vibrations of what? Energy carried by what? This is where it gets slippery. Because sound isn't a thing traveling. That's the first illusion we need to shatter. Nothing actually makes the journey from here to there. The air here doesn't fly over to become the air there. The molecules near my mouth don't rush across the room into your ear. That would be wind, not sound. So if the air itself doesn't travel, what does? And why do we need air in the first place? Here's an even deeper question. When you hear my voice, you're detecting something that happened in the past. The sound happened at my mouth some tiny fraction of a second ago. But what preserved it during that time? What carried the information that lets your brain reconstruct what I said? The answer isn't what you think, and understanding it requires us to look at what air actually is. Let's start with the right question. Not what is sound, but what is air? Because you can't understand how sound moves through air until you know what you're working with. You think of air as empty space, as nothing. Open your hand, wave it around, there's nothing there, right? Wrong, completely wrong. Air is matter. It's made of molecules. Mostly nitrogen, some oxygen, a bit of carbon dioxide and other stuff. Trillions and trillions of molecules in every cubic inch of space around you. Now here's what's wild. These molecules are moving, not drifting slowly, moving fast. At room temperature, air molecules are flying around at about 500 meters per second. That's over 1,000 miles per hour, faster than a jet. Right now, surrounding your face, molecules are screaming past each other at supersonic speeds, but they don't get far because they're packed relatively close together. A molecule might travel only about a 10 millionth of a meter before, wham, it crashes into another molecule, bounces off in a new direction, travels another impossibly tiny distance, crashes again, bounces, crashes, bounces, billions of times per second. This is what air is, a chaotic storm of invisible particles in constant violent collision. Now, when everything's balanced, when no sound is happening, these collisions average out. Molecules are flying in every direction randomly. At any given spot, roughly the same number of molecules are present from one instant to the next. The pressure stays constant. The density stays constant. Everything's in equilibrium. But here's the key insight. Even though individual molecules are moving incredibly fast, the average position doesn't change. The air as a whole sits still. No wind, no bulk motion. Just frantic microscopic chaos that averages to stillness. This is the stage. This is what sound has to work with. Not empty space, not a continuous substance like water, but a granular swarm of particles in relentless collision. So when I ask, how does sound move through air? What I'm really asking is, how does a disturbance in this molecular chaos propagate? How does a pattern in this randomness travel? Because that's what sound is. Not a thing moving, but a pattern moving through the chaos. Now let's create a sound. I clap my hands. What actually happens? My hands compress the air between them. Suddenly, violently, they push inward. The air molecules that were there get squeezed, compressed. Imagine a crowd of people standing around, each person moving randomly, bumping into neighbors occasionally. Now suddenly someone pushes a wall into the crowd from one side. What happens? The people near the wall get shoved closer together. The density of people increases in that region. They're compressed into a smaller space. That's what my clap does to the air. It creates a region of compression, a region where molecules are temporarily packed closer together than normal. Now here's what matters. When molecules are packed closer together, they collide more often. More collisions mean more force. More force means higher pressure. So that compressed region is also a high pressure region. And pressure wants to equalize. That's fundamental. High pressure pushes toward low pressure. Always. It's not a choice, it's thermodynamics. So what do those compressed molecules do? They push outward. They push on their neighbors. The neighbors get compressed, now they're at higher pressure. So they push on their neighbors. And this continues. The compression spreads, not because molecules are traveling long distances. Each individual molecule is still just bouncing around chaotically. But the pattern of compression, the wave of high pressure that moves outward, it propagates. Here's the beautiful part. After the compressed region passes, what's left behind? Lower pressure, because molecules pushed forward, leaving fewer molecules behind. So behind every compression is a rarefaction, a region of lower than normal pressure, lower density. And just like high pressure pushes outward, low pressure pulls inward. The surrounding molecules fall back to fill the gap. This creates another push, another compression ahead, and the pattern continues. Compression, rarefaction, compression, rarefaction, spreading outward in all directions from my hands. This is a sound wave, not a thing traveling, but a pattern. A traveling disturbance in pressure and density. The air molecules themselves just jiggle back and forth, oscillating around their average positions. Each molecule moves maybe a fraction of a millimeter, but the pattern, the wave, travels across the room at the speed of sound, about 340 meters per second. Think about that. Individual molecules moving at 500 meters per second in random directions, but the pattern moving at 340 in one specific direction. How? Because the pattern isn't carried by individual motion. It's carried by collisions. By the time it takes for one molecule to hit the next and transfer momentum, the speed of sound is really the speed of momentum transfer through molecular collisions. It's a collective effect, an emergent phenomenon arising from trillions of particles acting together. No single molecule knows about the wave, but together they create it. Now let's follow this wave to your ear. The compression pattern is spreading outward, a ripple of high and low pressure moving through the molecular chaos. It reaches your eardrum. Your eardrum is a thin membrane, a flexible wall. On one side, the air outside. On the other, air inside your ear canal. Normally, the pressure is equal on both sides. The eardrum sits still. But now the sound wave arrives. A pulse of high pressure hits the outside surface. Suddenly, there's more force pushing in than pushing out. The eardrum flexes inward. Then the rarefaction arrives low pressure. Now there's less force pushing in than pushing out. The eardrum flexes outward. High, low, high, low. The eardrum vibrates. It's being pushed and pulled by the oscillating pressure of the sound wave. This vibration is tiny. For normal conversation, your eardrum moves less than the diameter of an atom. An atom, the quietest sound you can hear, displaces your eardrum by less than the width of a single hydrogen atom, and yet your ear detects it. How? Because attached to your eardrum is an incredibly sophisticated chain of mechanical amplifiers. 3 tiny bones called the ossicles, the hammer, anvil, and stirrup. They form a lever system that amplifies the eardrum's motion. The stirrup connects to a fluid-filled chamber called the cochlea. Inside the cochlea are thousands of tiny hair cells, each tuned to a specific frequency like strings on a piano. When the fluid moves, the hair cells bend. And when they bend, they fire electrical signals to your brain. Your brain receives these signals and reconstructs the information: pitch, volume, timbre, direction. It interprets the pattern. And you experience hearing. But here's what's profound. What actually reached your ear? No molecules from my mouth arrived there. The air next to my mouth stayed next to my mouth, just jiggling. The air next to your ear stayed next to your ear, just jiggling. What traveled was pure information, a pattern encoded in pressure oscillations. The wave carried no mass. It carried no matter, just a disturbance, a ripple in the medium. Energy, yes, a tiny amount of energy transferred through collisions, but the essence of what was transmitted is information. The pattern of how I moved my hands, preserved and propagated through billions of molecular collisions, delivered to your ear. Your brain decoded it and knows a clap happened. This is what sound is. Information transmission through pressure waves in a material medium. It's not a thing, it's a relationship. A connection between a source vibration and a receiver mediated by the collective behavior of matter. And now you can see why sound needs a medium, why it can't exist in vacuum. Because without molecules, without collisions, there's nothing to carry the pattern. The information has no substrate to propagate through. In space, no one can hear you scream. Not because sound disappears, but because sound cannot exist without matter to vibrate. Let's dig even deeper into why air specifically works so well for sound. Why not water? Why not steel? Well, actually, sound travels through both. Through water at about 1,500 meters per second, much faster than air. Through steel at about 6,000 meters per second. The speed depends on two things: how stiff the medium is and how dense it is. Stiffness helps. If molecules resist being compressed, they push back harder, transferring momentum faster. That's why sound is faster in solids than liquids, faster in liquids than gases. Solids are stiff. Density hurts. Heavier molecules are slower to accelerate when pushed. So sound travels slower in denser materials if stiffness doesn't increase enough to compensate. Steel is both stiff and dense, but the stiffness wins. Sound flies through it. Water is denser than air, but much less compressible. Sound is faster. Air is a gas, very compressible, low density. Sound is relatively slow. But here's what makes air special for us. It's everywhere, it's cheap, and it's already the interface for our breathing system. Evolution didn't design our ears for underwater hearing. We're air creatures. Our ears are optimized for the impedance match with air. Impedance is resistance to wave motion. When a wave hits a boundary between materials with different impedances, some energy reflects, some transmits. Your eardrum and air have similar impedances. Efficient energy transfer. If you put your ear in water, most sound reflects off your eardrum. You hear poorly. Different impedance. Bad match. But there's something else about air that's profound. Air allows sound to spread in 3 dimensions easily. The wave expands as a sphere. Energy distributes over an increasingly large area. This is why sound gets quieter with distance. Not because the wave runs out of energy exactly, but because the same energy spreads over a bigger area. The intensity energy per unit area decreases with the square of the distance. Double the distance, 1/4 the intensity. This inverse square law is fundamental to how we experience sound in open spaces. And here's what's beautiful. Despite all the complexity, despite trillions of molecules colliding chaotically, the mathematics of sound waves is elegant. We can describe them with wave equations, predict how they'll reflect, refract, interfere, build concert halls with perfect acoustics, design noise-canceling headphones, all because we understand the pattern. We understand that sound isn't a mystery. It's pressure waves, molecular collisions, information propagation through matter, physics, pure physics at every level, from quantum mechanics governing how molecules interact, to classical mechanics describing wave motion, to thermodynamics explaining pressure. It all fits together. Reality is coherent. Now here's where it gets really wild. Everything I just explained about sound, the molecular collisions, the pressure waves, the information transfer, applies to your voice right now. As I speak, my vocal cords vibrate. They push air out of my lungs in pulses. Those pulses create complex patterns of compression and rarefaction, not simple waves like a clap. Complex waves containing many frequencies simultaneously, high frequencies, low frequencies, all superimposed. This complexity is what makes my voice recognizable. It's what carries language. The pattern encodes phonemes, words, meaning. And that pattern radiates outward through air, through billions of chaotic molecular collisions, and somehow arrives at your ear intact enough for your brain to decode it, to reconstruct my words, to understand my meaning. Think about that. Thought becomes muscle movement in my throat. Muscle movement becomes air vibration. Air vibration becomes a propagating pressure pattern. The pattern reaches your ear. Mechanical vibration becomes electrical signals. Electrical signals trigger neural patterns. Neural patterns become conscious experience. You hear my voice. You understand my words. A thought in my brain has been transferred to your brain using nothing but air molecules bouncing around. That's telepathy through physics. Communication is the most ordinary miracle. We do it constantly and never think about how impossible it seems. How absurd that wiggling air could carry meaning. But it does. And now you know why. Not because sound is magic, but because air is matter. Matter obeys laws, and those laws create patterns that can carry information. The universe is set up so that vibrations in one place can create corresponding vibrations elsewhere. Cause and effect propagating through space. Reality is connected, and sound is one of the fundamental ways that connection manifests. So, why does sound move through air? Because air is not nothing. It's a sea of molecules in constant collision, and collisions transmit force, and force creates patterns, and patterns can propagate. Sound moves through air because reality is connected, because matter interacts, because the universe permits information transfer through physical law. And here's what I want you to take away. Every time you hear something, you're experiencing one of the most fundamental processes in nature. Not magic, not mystery, but emergence. Complexity arising from simplicity. Trillions of particles, each following basic rules, creating something new, a wave. Information traveling, meaning transmitted. You don't need to invoke anything supernatural to feel wonder at this. The real explanation is more beautiful than any myth. Sound is molecular chaos organized into pattern, randomness shaped into message. The physical universe, speaking to itself, and you, with your impossibly sensitive ears and your incredibly sophisticated brain, are able to listen, to decode, to understand. That's what sound is. That's why it needs air. And that's why reality is so much stranger and more wonderful than we usually imagine. Now you actually know.